I hope you had a chance to watch this video here, Physics: A World in Motion, Fission and Fusion. I don't want a copyright strike on this, so watch that on your own leisure, and here are the corresponding answers to the question. And now you know about that. So let's decipher that video in a bit more detail. First off, the video talked about this whole thing about the mass energy equivalence formula. I'm sure you're used to that as E equals mc squared. But here in Canada, we like to be a little bit extra, just like how we like to talk about time as delta t, as you had to start at a certain time and finish off in order to have a difference in time. Well, E equals mc squared is technically the fluctuations in mass that results in energy. So anytime you have a substance and its mass changes even by the minuscule amount, that change in mass results in lots of energy being released, multiplied by an insanely huge conversion ratio. You can think of c squared as a coefficient. For example, y equals mx, where your value of m is 3,000,000,000. Too many zeros? Maybe another zero. That looks about right. Take that number and square it. That's the conversion ratio. All right, so a little change in mass results in bucket loads of energy being emitted. And we need to know a few more conversion values. Speed of light, that needs to be given, as well as this guy over here, which I'll discuss in a bit more detail at the end of this episode. Here are also other constants that you should know. With regards to U, what exactly is it? Well, U is known as AMU, atomic mass unit. What exactly is an atomic mass unit? Well, imagine the most common and abundant atom in our body, which is, that's right, we're carbon-based organisms. The most common isotope found in our body is also isotope number 12. So you take carbon number 12 and you slice it up like a pizza slice. Slice it up 12 different ways, and now you have 1 AMU. That's where the numbers come from. And this is the weird thing that scientists have noticed. If you take any given atom and you break it up into smaller constituents of protons, neutrons, and electrons, the mass of the individual entities will be greater than the atomic mass itself. And that's because it takes energy to hold the nucleus together. So that missing mass is the binding energy that holds the nucleus. You can also effectively think of binding energy as the additional energy you'll need afterwards if you want to break that nucleus apart. An electron volt is not a volt. It is actually a measurement used to describe small quantities of energy. By definition, an electron volt is the amount of effort required to move one lonely electron across two metal plates. If you had an electron and the electron was near to the negative plate, well, you know that electrons don't like other electrons, so the electron will want to move to the opposite plate, which is positively charged. And as long as this is hooked up to a 1 volt battery, then 1 volt times an electron will give you an electron volt. Work is equal to force times distance. So an electron volt is a measurement of energy, or the work it takes to move an electron across a voltage difference of 1 joule per coulomb, or 1 volt. I know it sounds weird, but this is how we can have a very small measurement. It's kind of like with regards to the American system. How many feet are there in a mile? I think it's 5820, or you know what, let me use the calculator, because this is the only way I can remember this. You got a farm. The field length is 660 feet. As long as you have that bull move back and forth, tilling the soil 8 times, there you go, 5280. So there are 5,280 feet in a given mile. To make matters worse, there are 12 inches in a foot. So that's how many inches there are in a mile. And if you want to deal this in mils, well, at least that makes a bit more sense. There are 1,000 mils per inch. Yeah, there must be 1,000. Yeah, 1,000 mils per inch. So that's how many mils there are in a mile. All right, not a very clean conversion ratio, and that's what this is as well. We have ordinary joules for quantities that you want to measure, like this guy. If this ain't big enough for you, maybe you'll want to measure it in calories. where a calorie is equal to 4186 joules, and a joule is equal to a joule. Or if you need tons of energy, then you'll measure it in kilowatt hours. That's a lot of joules. That's equal to 3.6 times 10 to the 6, or 3.6 million joules, 3.6 megajoules. But sometimes you have experiments that which a joule is just too big of a measurement. You just want tiny values of it. And that's where an electron volt comes into play. Because 1 electron volt is equivalent to 1.602 times 10 to the negative 19 joules. It's a very small measurement. And if that's too small, then you can upgrade it to 1 million electron volts, which is equal to 1.602 times 10 to the negative 13 joules. Now you know about that. Okay, so the mass of a helium-4 atom is specifically 4.00260 standard atomic mass units. What is its mass defect and binding energy? With regards to this particular lesson, you have to carry as many sig fig as possible, because if you try to round to the nearest whole, you're back to the last day's lesson. You won't notice a difference. You have to keep in mind that with this formula over here, E equals delta mc squared, you can't exactly just use the mass of a proton, neutron, or electron for m. We're talking about the same exact elementary particle and just fluctuating its mass by a smidget. And that's enough to emit off tons and tons of energy. Okay, so what is its mass defect? Now there's a difference between all of it combined together versus all of its entities. So all of it combined together is this value here, but the entities will have a greater mass than all of it combined together. So now you need to look up on that previous lookup table. Mass of a proton, neutron, and electron, and yes, you could measure it in AMUs. So we're going to use the AMU equivalence. So what is the total mass of it all separated? I'll let you work that out. Good. From the previous lookup table, you just have to crunch it in. And again, if you round to the nearest whole, you're not going to notice a difference. Try to carry as many extra sig fig as possible. The more the merrier. So you'll notice that these values do differ. That's where the mass defect comes into play. All right, the mass of all the individual parts will be greater than the mass of it all combined together because it takes energy to hold the helium nuclei together. That's your mass defect. As for the binding energy, well, how much energy is associated with this? Well, for one thing, with regards to U, that's a weird unit. You're just taking an atom of carbon, slicing it 12 ways. That's what it is in AMU. But we're used to measuring things in kilograms. So you have to look it up on the reference table, and there is a conversion ratio between AMUs and kilograms. So the first thing you're going to do is you're going to multiply the 0.03 by the conversion ratio, and you'll find out that works out to a very, very small quantity of mass. Even though it's small, you got to keep in mind that c squared is a huge multiplier. 3 times 10 to the 8 squared. So that will boost it up. 4.54 times 10 to the negative 12 joules. And if you want to measure it in electron volts, you can. Once again, if you missed out on before, because my handwriting was small, 1 eV is equal to 1.602 times 10 to the negative 19 joules. So 1 mega electron volt is to take this and multiply by 10 to the 6. So negative 19 plus 6 gives you negative 13 joules. All right, so you take this, multiply by that. Where's it divide? You gotta multiply by, no, divide. Divide by, yeah, 4.54 times 10 to the negative 12 joules divided by. How do I know that? Because you need to multiply by a ratio where you have joules downstairs and mega electron volts upstairs. So 1 MeV divided by 1.602 times 10 to the negative 13 will give you your 28 mega electron volts. There you go. So lots of energy is released in a nuclear reaction, regardless if it's fusion or fission. So how much energy is emitted? For example, how much energy is released per individual atom of uranium-235? Now let's say that this is the particular reaction that occurs. As I mentioned before, you won't know which one will occur naturally. I'll have to give you an example of it. So here's one example of the type of nuclear fission that can occur with regards to uranium. So the masses between before the reaction and after reaction are different. So we need to look for that mass defect before the nuclear reaction versus after the nuclear reaction, or after subtract the before. So we go through that. We carefully figure out the differences between the after versus before. Here's a hint. Whenever you're solving these problems over here, for the most part, your delta M will be less than 1. As a reminder, if you were to just add up the atomic numbers together, 235 plus 1, that'll give you 236. Guess what happens with 141 plus 92 plus 3, because it's 3 times 1? You'll get 236. You're not going to measure or discern any mass defect if you round to the nearest whole. You need to have this highly elevated, detailed information. Don't worry, you don't need to memorize it. It will be given to you in a lookup table. All right, what the exact specific AMU value is. So uranium-235 isn't just 235 anymore. It's 235 and change. And the same is also true with all the other isotopes. And that will have to be given to you in order to solve for these type of questions. So because it's a minuscule difference, your delta M will likely be less than 1. That's a good way to check your work. Now, if you want to find out the amount of energy released in joules, then I'll need to multiply this by that conversion ratio of 1.660 to convert into kilograms. And now I can name drop that into E equals mc squared and get my value in joules. If I want to divide that by 1.602 times 10 to the negative 13, it'll convert it into MeV if that's what I was interested in. But wait, what if there was a shortcut to all this madness here? Let's say that I wanted my answer in MeV. You'll notice I'm doing the same process over and over again. I'm multiplying by this. I'm multiplying by this squared. And I'm dividing it by 1.602 times 10 to the negative 13. So if you take a constant, you multiply by another constant squared, and then you divide by another constant, you're going to be left with, that's right, a constant. Here's where it is right over here. So let's say I wanted to convert this problem over here into an answer in MeV. How would I do that? Well, it's not that hard. E equals delta mc squared. If you look at this conversion ratio over here and you isolate for c squared, that's equal to 931.5 MeV over U. So anytime you see a c squared, you can just name drop that in. So 0.18667 U times, instead of all the other madness, we know that c squared is equal to 931.5, so multiply by 931.5 MeV over U. I'll have you work that through. And there you have it, the super fast way to get to the same answer. Work hard, my friends. It'll be rewarding. Catch you guys in the next episode. Or maybe not. How about we just do one example? Because, yeah, the chemistry question over here. All right, how would you find out how many joules is released per gram of U-235? If you haven't taken chemistry yet, none of this will make sense. We got to pull out that mole train now. So, what is the E over M ratio? Well, we need to do a bunch of conversion ratios to get to your answer. So for your chem folks, study this. I hope that makes sense. Will it show up on your next test? No. Unless if you're in chemistry class, then yeah, it's going to show up in your chemistry test. How about that? All right, catch you guys later.